Hello everyone. Uh, I would like to talk about how to use R for optimization and solving for zeros. So I will talk about how to solve for one unknowns and how to solve for multiple unknowns simultaneously. So the goals of this lecture is that some equations are not easy to solve, so I would like to introduce you how to solve it. And sometimes, even though you know how to solve the equations, but there is no closed form formula, so how to do it with R would be easier. So let's start with one variable problems. So there are two types of problems that we can use R to solve it. First, we would like to find zeros. We can use the function called uniroot, and we can find the maximum or minimums. We can use the functions called the nlminb or optim. So, as a first example, I would like to solve the following function such that 0 equal to x times the logarithm of x plus x squared minus 5. So note that this function is only defined when x greater than 0 because of the log function. So the uniroot function is used to find x such that it satisfies this function. So first, we need to define the function of the term on the right hand side such that the function, I call it function 1, is asserted as a function of one argument x. Then I put x times the logarithm of x plus x squared minus 5. Then I use the uniroot function to find x such that the outcome of the function is 0. So the uniroot, open the parentheses, f is a function equal to fun1, fun1 that we just defined it. And then I put the interval such that, okay, I would like to find x within this interval from 0.00001 until 100. So after I run that, I found that the root is 1.93, which is if I substitute x by 1.93 in the function, I will get the result of negative 5.7 times 10 to the power of negative 5, which is very close to 0, right? And the number of iteration is 16. So right now, yes, we know how to solve for 0 by defining a function. So let's plot it. I plot x is the sequence of 0.01 to 5 with the step of 0.01. This is the x-axis, and the y-axis I put the function 1 on the sequence and type equal L to make a line. Then I make the AB line such that I would like to have the horizontal line, which is y equal to 0. So you can see that the graph is has a monotonic relationship and has a function of x of 0. So, and you see the this point is around 2, which is 1.93 that we just solved it. However, if an interval does not contain any x such that function of x is 0, for example, I call uniroot function of 1 and I put 50 to 100, then the error will be provided such that, okay, uniroot cannot find the function of x equal to 0 because both endpoints are in the opposite sign. So sometimes within an interval, you have more than one zeros. For example, I have this function such that function of x equal to x uh, in the cubic term minus 3 times x squared minus 18x plus 40. Okay, when I plot this function as a sequence from negative 5 to 7 with the step of 0.01, and you see I put the function over here and type equal L, and I also made the horizontal line such that y equal to 0. You see that there are 3 sections inside the graph. Okay, over here, and over here. Okay, and you will see we have 3x 3x such that y equal to 0, negative 4, 2, and however it's supposed to be 5. Even though we have 3 zeros inside the interval, if we provide this interval, it will give you the first 0. It's only show 4, but it should have 2 and 5 as well. So every time you use uniroot, you need to be aware that even though you got the root such that f dot root is close to 0, it does not mean that u has only one 0. It could have multiple zeros. So let's move on to the next application such that I have the missing proportion okay, in the missing at random. So the missing value depends on auxiliary variables. So I used this relationship in the logarithm logistic relationship. So the log of the odd of the proportion of missing equal to the intercept plus the slope times the auxiliary variable, which is z. And I can shuffle the formula a little bit to get the right hand side. Let's say that beta 0 is not known and beta 1 equal to 0.7 and z is the binary trial. Binary trial means that it could take only 2 values, 1 or 0, and we have the proportion of 1 equal to 0.5. So obviously the expected value of z is 0.5. So we need to use the uniroot. So we need to isolate 0 on the left hand side and then put everything on the right hand side. And I write a function to solve that. So I got the function 2, which is a function of the intercept that I would like to solve, and I could provide the proportion of missing over here. So the logic of proportion of x equal to the intercept plus 0.7, which is a slope, and 0.5, which is the expected value of 0.5 of z. And then I put 1 over 1 plus the exponential of negative log x, all of them minus p miss. This one is exactly the same as this. And we would like to find the intercept such that this term equals zeros. So I put fun2 over here. The interval is from negative 5 to positive 5, and proportion of missing is 0.2. So every time I put the second argument in the function over here, you can pass the proportion of missing in the uniroot function, and then p-mit will be passed into the function 2 like this. So let's see the solution. You see that this one, the intercept, equal to negative 1.736, and we can plot the graph such that the intercept is from negative 5 to positive 5 with the step size of 0.01, and then the y-axis is b0, and I put the proportion missing of 0.2, and don't forget to plus 0.2 such that uh, this one will provide the expected value of 0, right? If b0 equal to negative 1.73, so we put 0.2 back such that y represent the proportion of missing. So you could see that 0.2, I draw the horizontal line over here. I see that beta 0 is negative 1.736, such that the proportion of missing is 0.2. Okay, let's move on to the next example, which is a little more complicated. So I would like to solve for the sample size in the independent t-test. So we can use the power analysis program like G star power, or in R we have the function called power.t.test to check it out. But this time we would like to solve it by writing a program. So we have the quantity of 0.5 that represents the standardized difference between two groups, and power is 80%, alpha is 0.05 to tell it, and I would like to have equal sample size. So in the power analysis framework, let's see the graph. We have the null hypothesis sampling distribution over here, and because the alpha of 0.05, each tail will has a proportion of 0.05 over 2. And we get the critical value on the right hand side, right? So we can draw the alternative hypothesis sampling distribution and make sure that the difference between the center of the null hypothesis and the center of the alternative hypothesis is 0.5 in the standardized scale. And we would like to highlight area to be 80% of the alternative hypothesis sampling distribution. So first, I need to find the critical value of the null hypothesis sampling distribution. So in the independent t-test, of course, the sample distribution would be central t distribution or standard t distribution, that when the center is 0 over here, and with the degree of freedom of the total sample size minus 2. Then we can get the critical value such that it has the proportion below this line as 0.975, which is equal to 1 minus 0.05 over 2, with the degree of freedom of n minus 2. So we can write down the critical value R code such that which is equal to Qt. Qt will change from the percentile proportion to the percentile point or the t value. So I put 1 minus alpha over 2 over here, and degree freedom is n minus 2. So second, we know the critical value over here. We would like to find the power, right? So the alternative hypothesis sampling distribution would be non-central tree distribution. So the center of the alternative hypothesis is not equal to 0. And the degree of freedom is n minus 2, and the non-centrality parameter or delta equal to d times the square root of n1 times n2 over n1 plus n2. But we know that we had equal sample size, so n1 and n2 are equal. So I can solve that and found that the non-central parameter is d times the square root of the overall sample size over 4, so which is here. Then I could find the observed power, which is the 1 minus pt, which change from the percentile point to the percentile proportion. Pt, I put the critical value over here, and then the degree of freedom is n minus 2, and non-centrality parameter is d times the square root of overall n over 4. I need 1 minus pt because pt will provide the value on the left hand side, but we want the value on the right hand side. So we need to have 1 minus pt. Okay, let's combine and write down the function. So I call it function 3. I have first the critical value over here, and this critical value will be used to find the observed power over here. Then I get the observed power minus the desired power and I want to make this subtraction to be 0 so that I can increase the sample size in the function over here to get the desired power. So I call fun3 in the uniroot function, and the interval of the sample size is from 5 to 1000. The coincidence is 0.5 and desired power is 0.8. This uniroot function will change the n value so that the power equal to 0.8. So let's see the solution. You see that the root is 127.53. So we would like to have the sample size of 128 so that we make sure that the power is just above 0.8. And you see the observed power minus the desired power is 6 times 10 to the power of negative 10, which is very close to 0. So next, I would like to make sure that I have only one solution, so I plot the sample size on the x-axis and power on the y-axis. Then, okay, the whole thing over here will provide the power. So I get this. You see that the cross section would be somewhere between 125, which is 128, which matches with our solution. So in the previous 3 examples, I would like to find x to get the value of the function of 0. However, in this example, I would like to find x such that it will minimize or maximize my function of x. So, for example, I would like to fit a distribution to a data. We would like to check whether data come from a particular distribution. For example, I would like to fit a distribution to data and check how likely this dataset comes from the distribution. We can use the likelihood function. Okay, so what does it mean? The likelihood of the parameter given the data point equal to the density distribution of x given the theta. So, for example, in the normal distribution, I have the proportion of x given mu and sigma equals to the likelihood of both parameter given x. So when every time we write the likelihood, it means that we know the data. We already have the data. We would like to find mu and sigma such that so we can plug in sigma over here and we can plug in mu over here to get the likelihood value of each data point. And if we have multiple data points, the likelihood of 2 parameters over here given the set of data points equal to the proportion of each individual data given the parameter mu and sigma. And because we have the assumption of independently draw, the proportion of the joint distribution of drawing multiple data points equal to its products. So big pi means that we would like to multiply the term inside the pi from I to n, because dealing with the product would give you very small decimal point and computer will break. So we would like to change it to the log scale, which is easier to handle in the computer. So I put log of the likelihood would be the sum of the log of the likelihood over here. This one I can write something like L mu sigma given x sub I. Okay? So we have the likelihood and maximum likelihood estimation is to find the parameter values for the example, which is mu and sigma, such that they maximize the likelihood function or the log likelihood function. So for example, find mu and sigma to maximize the likelihood, and to find the likelihood of the individual data we need the density function. D means density. So such as the norm, which find the density of normal distribution, or the chi-square, which find the density of chi-square distribution. So for example, I would like to fit a distribution to the rating variable in the attitude data. So it's had from 43, 63, 71, 61, 81, and so on. And I would like to check if I fit the data with the chi-square distribution with degree of freedom of 50, what is the likelihood of fitting that distribution, sorry. So I assign x as the attitude data, the rating variable from the attitude data, and then I use the chi-square x given the degree of freedom of 50, and I would like to use log scale, so I put log equal true, and I sum the chi-square, I sum the likelihood of individual data point. So the chi-square will provide you the likelihood of each data point, and I sum it to get the likelihood of the overall variable. So if I change the degree of freedom from to 50, 60, 70, 80, 90, what will I get? I get different log likelihood. So from 50 I get negative 144, for 60 I get negative 120, 70 I get negative 121, something like that. So the maximum likelihood would be right here, around here. So the chi-square with degree freedom between 60 and 70 is the most likely distribution under this rating variable. So to find the degree of freedom such that it provides the maximum likelihood, so it means that we would like to have the maximum likelihood estimate of the degree of freedom. We can use the nlminb function to get it. So I write function 4, which is a function of x, which is the degree of freedom, and that, which is a variable that we want to find the distribution underlying it. So this one is the sum of the log likelihood of the chi-square distribution. However, nlminb would find the minimum, not the maximum, so we need to put the negative sign over here to make sure that, okay, nlminb will find x such that the term, the result of the function is minimum. So in nlminb, I got the starting value of 5. Fun4 would be the function that I would like to minimize in this function. So maximize or minimize depends on the negative side or positive side you use in the result of the function. And we can put additional argument passed to the function. Also, we can put the lower bound and upper bound of x. I put degree freedom of 2 as the lower bound and 1000 as the maximum degree of freedom. So I need the negative resulting value because nlminb will find the maximum, define the minimum value. So let's see the result. So the result would have the resulting x is 64542. So which is the degree freedom is the most likely to fit in the data. And the objective would be 118.2136. And convergence 0, which means you successfully convergence. This is the number of iteration. So we got the result. Alternatively, we can use the optim function. The optim function is better than nlminb such that it could provide the Hessian matrix. Hessian matrix is used to find the standard error. However, the nlminb function has more consistent performance. So most of the time, the iterate how to find the solution, nlminb would be better. So the optim function is similar to nlminb such that we put the static value over here, these are the function over here, also the additional argument that we use. We can put the boundary such as lower equal to, upper equal to 1000. And if we want the boundary, we need to use the method of L-BFGS-B, which is the method that the optim function use when we have the boundary, the lower boundary and upper boundary. And Hessian equal to is that, okay, we want to get the Hessian matrix. Okay, L-BFGS-B method for optimization. We use that because we have the lower and upper bounds, and we also ask for the Hessian matrix. The result of the optim function, you can see that we got the degree freedom of 10.17. This one is so different to nlminb that we got 64, right? And the value over here would be 1166.63, which is much more than the previous results. Okay, so let me go back, and okay, this is a resulting x which is not preferable, and the minimum value of the function of x which isn't good, right? It is 1166.63, which is much higher than what we got from the nlminb function. 0 means successfully convergent. It does not mean that you get the global minimum. Okay? And the Hessian matrix is over here. So let's pretend that this one is the desired answer, and we would like to find the standard information matrix, okay, which is the variance of the parameter is the inverse of the Hessian matrix. So this one, or we can use the variance of the predicted variance of the parameter is the inverse of the Hessian matrix. But if you go to the statistical textbooks, you see that the feature information matrix is equal to the negative sign of the inverse of the Hessian matrix. However, we already provide the likelihood function that we want to find the minimum, which has the negative sign. So that's why we don't need the negative sign in over here. Okay. So we can save the result of the optim function to, let's say, fit, and then the information matrix is assigned as the inverse of the Hessian matrix from the result, and we got the information matrix equal to 0.046. We have only one element because we had only one parameter. And then the standard error is the square root of the diagonal element of the information matrix. Okay, so the standard error would be 0.214, and we can use 0.214 to find the confidence interval. So the confidence interval would be the estimate plus or minus the critical value times the standard error, right? We can write it out, and then we get the confidence interval of 9.75 and 10.59. So you can go back to see the script later. Okay. So I would like to say that you see that the nlminb function provides you the, I think it provides you the global minima, which is consistent to the value that we manually manipulate from the freedom of 50, 60, 70, 80, and 90, right? However, the optim function provides you the local minima, which is not good. So let's make another example to examine what is going on. So I have this function x to the fourth plus x to the third minus 3 times x squared plus x plus 2. And I got this graph, and you can see that I have local minima over here and global minima over here. If I write out the function like this, and I use nlminb with the starting value of 2, I get 0.77 over here. But when I start with negative 2, I got negative 1.71. You see, we get two different results. However, the left hand side would be the local minima because it's equal to 1.79, and the right hand side is global minima because it's equal to negative 4.93. So every time we use nlminb or optim function, we need to make sure that we use different starting values to avoid local minima. Okay? So the fifth example, let's say I would like to find the factor loadings, and I specify the factor loading to be negative 5 times k, negative 6 times k, negative 7 times, no, 0.5k, 0.6k, sorry, 0.7k, 0.8k, and 0.9k. And then I would like to fix the error variance such that indicator variance are 1. So, and then I would like to find k such that the reliability is 0.8. So this is the factor analysis model, and you see that 0.5k, oh, this is supposed to have the square, sorry, square and square, to make sure that the indicator variance are 1. And then I got this. So this is a reliability formula from the previous lecture. And I need to isolate 0 on the left hand side. So let's go to the function. I write the function such that I have k and the target reliability, like so loading is k times the sequence of 0.5 to 0.9 with the increase of 0.1. That is, we have 0.5, 0.6, 0.6, 0.7, 0.8, and 0.9. Okay, and the error would be 1 minus the loading square, which make the indicator variance equals 1. And then the omega is the sum of the loading square divided by sum of the loading square plus sum of the error variance, as we have the formula previously. And then omega minus target, which is the function of the k that we would like to have, is equal to 0. So uniroot find loading, and the range of k would be from 0.1 to 1.5. The target reliability is 0.8. Okay, and you can see that k is equal to 0.94. Okay, and the resulting function would be very close to 0, which is very good.